I very much appreciate that you are all here in this early morning session on the last day and after this great conference dinner on the boat and the party. So thank you very much for coming. I was asked to give an overview of recent developments in mountain permafrost research. And actually I wanted to start with kind of a number, how much permafrost is out there in permafrost regions. And this is actually not so easy, as we also learned from the publications by Stefan Gruber. So it depends very much on the definition of what is a mountain. So I'd rather want you to just sit down, have a look at this beautiful landscape we see in many mountain areas, and have a look at what are the typical characteristics of mountains, and how can we learn something about the occurrence and state of permafrost in mountain regions. So if you look at this landscape here, there's actually a view in the Swiss Alps, of course. You see here the dome, which is the highest peak, which is entirely situated on the Swiss terrain. You see several mountain ridges, so you see the large-scale topography and also small-scale topography. You can actually see here that we are in a cryosphere environment with these poor little glacier we see up there. We see some snow remnants, so the photograph was taken end of August, so maybe perennial snow patches, and we see landforms, actually rock glaciers sitting here in the valley bottom, and these landforms tell us that there's permafrost around, so they are indicators for the occurrence of permafrost. And in mountain areas where we don't have enough data, or we don't have so many data on the temperatures at the surface or the ground, we can use these morphological indicators to get an idea of the permafrost occurrence and also the extent and the status. So we heard several presentations during the conference, for example, from the southern Andes, and also from the Himalayas, where they use these landforms, they map these landforms to get an idea of permafrost extent and start to model the permafrost distribution. So when we speak about mountain areas, the most important characteristic is the topography and the spatial heterogeneity in this topography. So when we look here, we see peaks with bare rock, we see different expositions, you see the shaded area here, you see differences in substrate like fine-grained material here, coarse-grained material. So we come up with this spatial heterogeneity as one of the main characteristics in mountain areas, and also especially influencing the occurrence of permafrost. So the topography influences the microclimate, the thermal regime at the surface as well as in the ground, and this also influences mechanical and also rheological regimes. So the high spatial variability with respect to nearly all surfaces and subsurface properties. And this makes it so difficult to measure the permafrost in the areas and also to model permafrost in these areas. So to sum this up once again, mountain permafrost is a function of topography, of course the climate situation, also hydrology. We have a lot of 3D effects, and if you see here, we have several landforms that should be analyzed also in combination. So we should not only look at what is going on in the rock wall here, or on the rock glacier here, or the moraine which is situated below, but we should see the entire slope with the different characteristics. And I think we have to mention, we also heard that in several talks, for example, by Anna Haberkorn yesterday, that the snow cover is one of the most, say, nervous interfaces in the system. So we have this topography which is influencing also the extent, the duration, and the thickness of the snow during wintertime. And this is very much influencing the occurrence of permafrost and the spatial heterogeneity. So that was already mentioned by Gruber and Haberle in 2009, that Mountain permafrost is invisible, extremely variable and heterogeneous, difficult to measure, difficult to model, and it currently undergoes rapid changes. So why are we working here when it's so difficult? And we could see during this conference that there were a lot of new measurement techniques that helped us to at least go for the difficult to measure and difficult to model. And I want to thank especially the conveners of this session on new frontiers in mountain permafrost research, because we got a nice overview on new technologies, how we can gain better information, new data with higher spatial and temporal resolutions, which allow for better process understanding and better description of ongoing changes. Of course, we also have to view this a little bit difficult in some areas. For example, in the Alps, you will see a lot of examples from the Alps later on. We have a lot of data available now, and when we get questions how we can continue, we always say, okay, we need even more data and more data and more data. And I think we have to really start getting the best of the data that we have for this process understanding. So from 1D to 4D, I shortly want to go through this because we have different informations from the ground. We have point information, we have snapshot information, like, for example, this borehole data that you see here on the right side from Rock Glacier Motel. I will show that again later on. Or, for example, just one BTS measurement that can give us information on is there permafrost in the ground or not. We have 2D information on permafrost extent. You see here, for example, the permafrost distribution map for the Swiss Alps, or you know from Stefan's work about this global modeling approach where we get information on the permafrost probability, here shown for the Himalaya region. And we have 3D information, landforms, including the underground, where we can conclude if there's permafrost and what is the status of the permafrost. But mostly we are interested now in the processes and also the changes in time. So, of course, in view of permafrost degradation, but we also have areas where we have permafrost aggradation. And here it comes to the point that the long-term monitoring is important. We don't need only snapshot data, but we want to have long-term series to have an information, how is the evolution of the permafrost going on. And I want to show you several examples, mainly from the Alps, where we gather this information. So this is an example from Andreas Kellerer from the Austrian Alps. He has several sites where he's investigating the ground surface temperature, mean annual ground surface temperatures in these regions. Here you see two examples from these two sites. You see the change in mean annual ground surface temperature over a period of nearly 10 years. This is one information we have from several sites. Of course, not also in the Alps. We have quite a good network in the Scandinavian countries also. Second, we have borehole temperatures, ground temperature information from different depths. You see here the series of boreholes that we have in the Swiss permafrost monitoring system. You will hear more about these data later on in a presentation given by Janet Netzli. On the left-hand side, you see the data from a depth of around 10 meters, and on the right-hand side, around 20 meters, and for Matterhorn, it's actually 30 meters. So you see over a period of, the longest series is starting in 1987. So over this period, you see the annual fluctuations, the seasonal fluctuations, and the development, which is even more better on this side with the depth of 20 meters, the evolution of the temperatures in the ground. You see that we have sites where the temperatures are lower, for example, at the Matterhorn or the Stockhorn sites, these are higher up, and we have several rock glacier sites. Based on this data, we can also monitor the active layer depth. Again, an example from Rock Glacier Motel. You see it was fairly stable over several years. And only recently we recognized that the active layer is increasing. Then we have sites where we look at more special extents, for example, in rock walls. This is an example from the work by Samuel Weber. He instrumented, maybe you remember when you've been to Zurich at the conference, there was actually during the conference the detachment coming out of this rock, exactly in this area. And you see it here. This is the area, the scarp of the 2003 event. And actually, they went there and installed different measurements up here, not only temperatures in the depth of 85 centimeters, but also crack meter, 2 axial and 1 axial crack meters. You see here the different devices, how the setup is, and the different sides of this mountain ridge. And they actually have quite a series of data now from 2009 to 2016. You can see the temperature from different places, expositions, south, east, and north, and blue. You can nicely see that, and you can see the development, the deformation measured in these fractures. This is the deformation perpendicular to the fracture in this slide, and the deformation along the fracture. And you see different signals. Some of them show more or less no development. Some show the annual cycle, or the annual cycle here, but go back every time. And some show development in the opening of the fracture, which is nicely visible here. Long-term measurements are also needed not only for the temperatures, but also for other subsurface characteristics. So we want to know how is the ground characterized. What is the amount of rock and air? If we have debris landforms, we want to know how much ice and how much water is in the ground. And the only, beside the borehole, so the point information, the only measure to deliver data on this is geophysical sounding. So there's also electroresistivity tomography, monitoring applied at several sites in the Swiss Alps. You see here the example from the Schilthorn, situated in the northern Swiss Alps. It's quite a long series from 1999 to 2016, and given here the mean specific electroresistivities and the changes over time. And as Christian also presented during this conference, they can calculate the characteristics of these different phases, like the rock content, the ice and water content, and the air. And they, over the period from 2008 to 2015, could show that at this site they can quantify the ice loss to about 15 to 20% of the former volume. Then, besides the surface and subsurface information, we also look at landforms and their changes, because we recognize that the landforms that are moving, they not only show that there's permafrost around, but they also react to changes, to temperature changes. So several years ago, they were monitored by repeated aerial images. Nowadays, we also go there every year and do terrestrial measurements to compare this. And here's just a snapshot from UAVs or drone measurements from 2014 to 2015. You see the annual rates on this, the flow fields on the rock glacier Morail, situated in the Engadine. You see this nicely flow fields. We have the highest velocities up here, 1.5 meters to 2 meters per year. We also have this small lobe, which is this breakout lobe here. And the long-term monitoring showed that the flow field stays more or less the same over time. So the highest velocities we see always on this lobe here. But the rates are changing over time. So we saw this also, the sketch from the permosites, that these are related to temperature developments and especially weather anomalies, such as the warm summer 2003, and also we see it from last year. So we have this spatial information on the flow feeds of the rock glaciers, of several rock glaciers. We also look not only at the horizontal changes, but also at vertical changes. Here again, this is the Motel rock glacier site. You see the vertical changes over a period of 6 years. And what you nicely see here is the movement of this furrow and ridge topography. This shows us this pattern of lowering and upgoing. What we also see at several sites now recently is kind of a subsidence signal on the rock glacier. This rock glacier next to Motel is quite of a different case. We see subsidence everywhere over the landform. But this signal in the routing zone of the rock glaciers is quite often measured recently. So in addition to this spatial measurement using aerial images or drone images, we also go there at least annually to have some high precision data with the total station or the DGPS. And you see here the annual horizontal velocities monitored over this profile from the routing zone to the front. Actually, rock glacier Motel is moving quite slowly, between 5 and 15 centimeters. But we also saw here now in the last 2 years that it is accelerating. If you want to know more about the processes related to these changes in movement, we are somehow limited when we have only these annual measurement, annual surveys. That's why another project was built up by Jan Beutel, Stefan Gruber, and others, and they set up GPS stations on several landforms, starting in the Southern Alps, but it's now more or less distributed over other landforms all over Switzerland. And with these measures, they are able to get much more higher resolution on the movements. Here you see a sketch from Diro rock glacier from Vanessa Wirtz. They monitored the temperature over a 3-year period, and also the velocities given in meter per day. And what was nicely visible that we have here the winters coming up. This is the season of the snow cover. Then we have the zero curtain and the summertime, and again the snow cover. And you see how this rock glacier is behaving. It is decelerating in the early winter, going down until end of winter, and then suddenly with the zero curtain phase, the velocities are going up. Then at some places we see also single events can be related to storm events. And this rhythm is nicely visible now with this long-term high precision data. So again, it's deceleration in winter, and directly with the zero curtain phase, velocities go up. This coincides well, of course, with the temperature we see and with information on the snow cover. With this information, we can go much more into detail concerning the processes. So it's not just that we measure, okay, rock glacier velocity is increasing, but we can see the development over the year and think about the processes that are going on in the interior. Besides this normal creep behavior and also the kind of degradation that we see with the subsidence that we measure at some places, we have also some landforms that show clearly destabilization. So we have distinct changes in landform geometry, high horizontal velocities, and then subsidence in southern part. We see in this example here, there was nothing that was like a normal rock glacier still in the 90s, and then it started to build up a crevasse in the routing zone here. This developed and deepened up to 14 meters. And you see that the entire mass is moving down and building up this active front here, which is actually like a landslide. So we see these forms, and we have several examples also from the Austrian Alps, where it became visible that it started already in earlier times. So this is not so much related to the recent warming that we observe, but we still have to have a look at these landforms. What we observe, there was a project by Sarah Springman She were able to drill some boreholes here and have a look. So it's very warm permafrost conditions. We see shear horizons at various depths. And also here we could conclude that the water in the system plays quite an important role. So all these, or most of these information go into the monitoring. As I said before, you will hear about this in another session by a talk given by Janet Nötzli. So it's a continuous long-term observation that we need from different characteristics like surface, subsurface, and also from the landform kinematics. To bring this long-term information into the future, sometimes we have to renew measurement stations. So I brought quite a lot of examples from the motel site, and we were always aware that this borehole might collapse in the future. It was drilled already in 1987. You can see a picture of this here, and we were always thinking, okay, maybe it will collapse or shear off, and then we lose this valuable series of subsurface temperature, of ground temperatures. So there was money available, and we were able to drill a new borehole last autumn. You see some pictures here. So we have a new borehole of 60 meters depth right next to the old one. We were able also to take out some cores, actually 26 meters of ice cores. We also saw that there was a water pocket down below the shear horizon, and we are now pretty happy about what is coming out. So see the first data and the comparison of the old and the new borehole in the sketch, just a sketch here from the winter time, but also here from 1st of June and from February, you nicely see the coincidence of the two boreholes. So it's also good control on the old data coming from the old borehole, and we are very happy that this worked out quite well. In addition to the temperature measurements, we do also deformation measurements in the borehole. And this is also now the very first data we can show you. So we have, it started with the filling in the sand in the borehole in January, and up to now, up to 1st of June, this is a wrong date here, we could measure nearly 4 centimeters of movement. Main part of the movement is occurring here in the shear horizon, as you can nicely see. We also did a scan within the borehole. Unfortunately, it was quite dirty after the drilling, but we have some information on the subsurface structure, the ice content, and also the boulders and the sediment inside. This again a picture from the boreholes, from the ice cores that were taken. As I said, we have around 26 meters, and they are now waiting at Alfred-Wegener-Institut to be analyzed. So we hope for some information on the age of the ice and to do an analysis of the long-term development of the landform. So it's not only the monitoring that helps us learning more about these environments, but also, of course, the science. So sometimes it's a good coincidence of monitoring and science, and sometimes, we have some specialties like here. So with this, I want to sum up that we observe warming and vanishing of permafrost in mountain regions, and we see impacts on the hydrological cycle, impacts on landform dynamics, impacts on rock wall stabilities and sediment transfer systems. I didn't go into detail here, but we heard a nice talk by Marcia Phillips yesterday. So there is a potential for higher frequency in landform, in rock falls, for example, and of course impacts on infrastructures and societies. So mountain permafrost undergoes rapid changes, and we can easily see also the sensitivity. So what are the future challenges then? So I think one point, we saw a lot of data now which is concentrated in the Alps, and we know that there are areas in Scandinavia that also have quite good data series and long-term monitoring series. But as we see here from the GTNP sketch, we have some lack of data in some of the mountain regions. especially the Andes and also the Himalayas. So I was quite astonished about this network. You see all the boreholes that are available, and Boris highlighted those that are above 1,000 meters to give some idea of mountain permafrost, and you can even see how long the data series are. So the red spots are up to 5 meters, blue up to 5 years, blue up to 10 years, 20 years. So you see that there is some long-term data, long-term monitoring series around, but this could, of course, be improved. So one aim should be the enhance of data richness, especially in mountain regions. Concerning the processes, I think we should continue quantifying and describing the changes in subsurface characteristics, like so that the changes in ice and water content. And here it came up that the water plays an important role at several sites, but there's not so much information around. So it's fairly hard to measure and model the water flows in these systems. And we want to show what are the normal processes, what are the signs of degradation, I'm finishing up, and where do we see destabilization. And of course, assess the related impacts on also other disciplines like the hydrology, geomorphology, and ecology. And finally, I think we should open more for a more holistic understanding, making use also on the neighboring disciplines such as hydrology, glaciology. We also heard talks on mountain permafrost and glacier interaction, or permafrost and glacier interactions, and also the biology. We saw several talks about that. And since we're here in the vicinity of Berlin, I think Alexander von Humboldt is quite a good example, because he was one of the first explorers combining different disciplines. Of course, he was concentrating on vegetation and vegetation geography, but he was also looking at different physical processes. He was mapping the snow-covered areas, and he actually compared different mountain ranges. So I think coming from the point information and the long-term series at the point, we could also open and discuss with other disciplines to actually characterize the changes we are facing in mountain permafrost areas. And with this, I'd like to thank you for the attention. I'd like to thank to my colleagues that provided ideas and data for this presentation. Thank you.